and Einstein and the people that came up with quantum theory kind of reign for a while, is as of right now. So that's what we're going to be looking at. Is we're going to be explaining to you through Mitch Stokes anything to do with quantum theory or relativity.
Yeah. So he says, although Newtonian mechanics is an excellent approximation for medium-sized dry goods at velocities far below the speed of light, when we address the most fundamental aspects of physical reality, when the universe redlines, he tells us, physics becomes an extreme sport, and we need quantum mechanics and general relativity. Right. So Newton does. I'm sorry, Lord Calvin, right? You were wrong. Newton was not the be-all and end-all, right? In fact, we progressed beyond Newton in the early part of the latter part of the 19th, early part of the 20th century, where quantum mechanics and general relativity were developed. He says both of these, though, they need one another. Neither of them, notice this, neither of them can account for physical reality alone. Right? So neither quantum mechanics nor general relativity can work on their own. So quantum mechanics talks about the very small, right? General relativity talks about the large, and the very large, and even medium sized. Newton is okay for medium sized stuff, right? But when you get beyond that, or you get way, or in terms of very large, like black holes and all that kind of stuff,
Stars,
and you get below that in terms of these quantum particles, Newtonian physics fails us, and so we have these two theories now
that work for different aspects
of reality, right? But the problem is, and he calls this section in the book a strained relationship, right?
So again, look back at what Calvin is saying, what Newton probably understood is, hey, he was a little bit probably on the spectrum, but he probably thought, I finally cracked this code with this calculus deal, and so this dark clouds thing, it's there, but we're kind of treating it as we'll eventually get there. We're in the early stages. We're now in that period of we got it figured out. Look, we've got the atom bomb, we got the computer chip. We're able to photograph with mathematical certainty a black hole. We're able to test the bending of light in gravity. This is amazing. But here, as you're saying, the two are diametrically opposed to each other, but we kind of consider it as science. It's true. It works. It's the truth. We've got there. It's just we kind of got to work out the middle. So it's the opposite of what Newton is. So maybe the next one will factor in all three.
So he tells us our two pillars, that is quantum mechanics and general relativity, are logically incompatible, right, with one another. And so at least if that's the case, then at least one of them has to be wrong, right? I mean, if they're logically, they tell us different stories, he says, about the unobservable world, right? So, although, they both work within their domains, they don't work when you try to apply one in the domain of the other.
Right.
And so we know that one, either they're both, wrong, or at least one of them is wrong, and we have to figure out a way to make these things work together, right? So he says, but he tells us few outsiders have heard of the irreconcilable differences between general relativity and quantum mechanics. And then he quotes Brian Greene here. He says, in all but the most extreme situations, physicists study things that are either small and light, like atoms and their constituents, or things that are huge and heavy, like stars and galaxies, but not both, right? This means that they need use only quantum mechanics or only general relativity, and can, with a figurative or furtive glance, shrug off the barking admonition of the other, right?
Right.
So I'm focusing on quantum mechanics, you're focusing on general relativity, and they work in the areas that we're trying to focus on, right? Either quantum mechanics with its very small atoms and all of those little subatomic particles and that sort of thing, or the very huge and heavy stars and galaxies that we work general relativity in. But and so mine works, right, and yours works, but not together.
Right. And for 400 years, we've been teaching elementary to college-age students the middle, and so everyone's able to do that old Newtonian mechanics, and so the medium kind of gets lost in it because everybody can do that. So that's not the cutting edge of science. You have to be able to come up with weird equations with letters instead of numbers.